atomic spectroscopy. When atoms or molecules absorb energy, that energy is often released as light energy. And this is the source of a lot of fun things like fireworks and neon lights. And so we're going to learn about what causes that. When the emitted light is passed through a prism, we see a particular pattern of wavelengths of light. We don't see a continuous rainbow like we do for light from an incandescent light bulb or from the sun. We see a pattern of wavelengths. And that's called an emission spectrum. And it's unique to the atom or molecule that's being excited. So it's not continuous. It has bright lines at specific wavelengths with a lot of darkness in between. It can be used to identify an element. And this phenomenon cannot be explained by classical physics. So here are pictures of I can't count today, three lamps: mercury lamp, helium lamp, hydrogen lamp. These are a lot like a fluorescent light bulb. There's a gas inside and there's an electric current going through that provides energy to the atoms or molecules inside, and then they get excited and they give off energy as light. For mercury, we see this blue glow. Helium gives off kind of a purplish, pinkish glow. And this is hydrogen's more of a reddish glow in this picture. I think the colors are a little weird on here. But different elements, different colors. We also see this if we put a solution of an ionic salt in a flame. It's called a flame test. And you can get some really cool colors. Sodium gives off a really bright light. It's characteristic orange-yellow. Potassium is this beautiful violet. It's kind of hard to see, so they got a really nice picture of it here. Lithium's bright red. Barium, it's just a real brief flash. It actually has kind of a greenish tinge. But this is also a way that you can identify these different elements by the color that they give in the flame test. And this is the same sort of thing that's happening in the fireworks. So the different colors that you see in the fireworks are due to different elements. So if we take the light from the hydrogen lamp, pass it through a slit in a prism, we do not see a continuous rainbow. We see three lines and a lot of darkness in between. This prism is separating the light just like it did with the light from the sun or from the light bulb, separating it with the red over here and the violet over there. The difference is this light only contains light of three different wavelengths, and there's nothing in between. It's not a continuous spectrum. Here's a picture of helium spectrum. The barium spectrum has more lines. This is what white light gives us. It's a rainbow. And here's oxygen and neon, and these are more complicated. But again, they all have bright lines with dark in between. This was observed and was very puzzling to scientists because, like I said, Newtonian physics can't explain what's going on here. That's an emission spectrum where you excite the element and it gives off light. You can also have the reverse, an absorption spectrum, where you can shine light at it and it will only absorb light at certain frequencies. And so the absorption spectrum and the emission spectrum are opposites of each other. So instead of bright lines, we have dark lines. And both of these can be used to identify elements. Johannes Rydberg lived around the turn of the 20th century. He looked at these atomic spectra and found that he could describe them with an equation. When you think about this guy measuring all this stuff and then figuring out an equation. This equation looks a little complicated, but it's actually remarkably simple. So here m and n are integers. 1 over m squared minus 1 over n squared, that quantity times r, a constant, is equal to 1 over the wavelength of the line. So this was really cool. It described the lines that were observed. But it gives little insight. It doesn't explain why the atomic spectra are discrete. It doesn't explain why atoms are stable. And he didn't even understand why his equation works. It works, but why? So not all that useful. Which leads us to Rutherford's nuclear model of the atom. In Rutherford's model, the atom contains a tiny dense center called the nucleus. The nucleus is essentially the entire mass of the atom. The electrons are so small that we just don't even have to consider them very much. The nucleus is positively charged, and the amount of positive charge balances the negative charge of the electrons. The electrons are moving around the empty space of the atom surrounding the nucleus. How the electrons are moving is really the big question. So that's a review of things we've talked about before. Problem with this model is that electrons are charged particles, and they're moving. And according to classical physics, a moving charged particle gives off energy. So if these electrons are giving off energy, the atom should be glowing all the time. Everything should be glowing because it's giving off energy. But they're not. And the electrons, because they're giving off energy, must be losing energy, and they should crash into the nucleus and the atom should collapse. Classical physics cannot explain why atoms are stable at all. But they are stable. The electrons don't crash into the nucleus. The nuclear model of the atom also doesn't explain what goes on when an atom gains or loses energy and how these lines occur. So Niels Bohr came in and developed a model of the atom that explained the changes that occur when energy is absorbed by the atom. And the major idea here was that the energy of the atom is quantized. The amount of energy in the atom is related to the electron's position in the atom. So the electron, if it's in a different place, the atom will have more energy, and if you move it back, it'll have less energy. Quantized is an important concept here. It means that the atom can only have very specific amounts of energy. We have lots of examples of quantized things in everyday life. A set of stairs is quantized. You can stand on the first step, you can stand on the second step. You can't stand in between. Or the rungs on a ladder. You can stand on the third rung or the fourth rung. You can't stand in between. It's quantized. Continuous is more like a ramp where you could go up just a little bit or you could creep up a tiny bit higher. You could be at any distance above the ground. But the energy of the atom is quantized. There are discrete levels. Like you can be in first grade or you can be in second grade or you can be in third grade. There's no 3 and a third grade. Not at any school I've ever heard of. So according to the Bohr model, the electrons are traveling in orbits. These are stationary states that are at a fixed distance from the nucleus. The energy of the orbit is also fixed. So the distance from the nucleus is fixed. It's a lot like the solar system. So you have electrons orbiting the nucleus like the planets orbit the solar system. The energy is fixed or quantized. Electrons are going to emit radiation or light when they jump from an orbit with a higher energy to an orbit with a lower energy. And the light that's given off is a photon of light. Remember, a photon is a packet or a piece of light, a particle of light. The distance between the orbits is what determines the energy of the photon that's produced. So bigger distance between, bigger change in energy, more energy in the photon. I'm going to jump ahead to this picture because we need a picture. So here's a picture of part of a Bohr model. So here's the nucleus, and here's the orbits. There's n equals 1, 2, 3, 4, 5. The electron would normally be in the lowest energy orbit, which would be the closest one to the nucleus. But if you zapped it with electricity or heated it, you could cause the electron to jump up to a higher energy orbit. So maybe it went up to n equals 4. It's not going to stay up there. It's eventually going to come back down. When it goes from n equals 4 back down to n equals 2, the energy that it absorbed has to come back out because of conservation of energy. It can't just disappear. So it absorbed energy to get up to here, and then when it goes back down, if it's going from 4 to 2, it's going to give off an amount of energy that's equal to the difference in energy between these two levels. And that happens to correspond to a blue-green light with 486 nanometer wavelength. Remember, the wavelength is related to the energy of the atom. And so by measuring the wavelength of the light that's given off, we can calculate the energy difference between the two orbits. pretty cool. What's kind of hard to get your mind around is that the electron is never observed between states or between orbits. It's in one or it's in the other. It's not even briefly traveling between them, and this is what's called a quantum leap. There used to be a TV show called Quantum Leap, right? And the guy would just be somewhere, and then suddenly he'd be somewhere else, right? Quantum leap. So electrons make quantum leaps. The energy that the photon emits is the energy difference between those two states. And we can calculate that from the wavelengths. I already said that. So the Bohr model has great historical and conceptual importance. And it's nice because it's easier to visualize, right? We know what the solar system looks like. We can picture electrons going around the nucleus. We feel okay about that, right? Unfortunately, it only works for atoms that have one electron, which would be just hydrogen, right? Everything else has more. So it didn't work for those. So it was replaced by the quantum mechanical model, which I'm guessing you have similar feelings to Bohr and Schrödinger and Einstein about the quantum mechanical model, that you probably don't like it, right? Because it's hard to think about. Thinking about the Bohr model is easier, and you're welcome to think about what the electrons are doing in terms of the Bohr model, as long as you keep in mind this isn't actually what's happening. This just makes it easier to think about. They are jumping up in energy, absorbing energy, and then coming back down, but they are not traveling in nice little orbits around the nucleus. Does anybody have any questions about all of that? Are they constantly jumping? That's a good question. No. They're only going to jump up if they get energy, if something gives them energy. Like if you have the hydrogen lamp with the gas in the glass tube and it's turned off, they're all just pretty much going to sit around in their ground state. When you turn the electricity on and start passing electric current through them, then they're going to be jumping up and down, up and down, up and down. So they only jump up if they get a right amount of energy to come in. Any other questions?
So they can't stay like in the fifth orbit?
They don't stay. That's called an excited state, and it's not very stable.
Oh, okay.
I think of it like this. I have, I do have two teenage boys again. Teenage boys. Okay, their natural ground state, the position you're most likely to find them in is horizontal. They're either laying on the couch watching TV or they're laying in their bed doing something on their phone, right? That's like normal. And then occasionally they have these bursts of energy and they get up and they go to football practice, or they go out and mow the lawn because you made them, but then they come back to the ground state. They can't sustain that, right? So that's how I think of the electrons. They get this burst of energy and then they go back down. Energy comes in and then it comes back out. Does that help?
Yes.
Any other questions?